So these are the topics. So we studied the structure optimization, and the structure analysis uses numerical methods such as finite element method, and in this work we use isogeometric analysis. And the algorithm used are heuristics because they are less susceptible to be trapped in local minimum, and it's not required to have the gradient information. However, they need a high number of evaluation, which can be a major hindrance when we employ high fidelity models. So we present an alternative to reduce computational costs, the surrogate models, that they aims to approximate these high fidelity models, and we use them to assist the optimization. So we focus on functionally graded plates that present a continuous and smooth gradation through the thickness direction. And we employ a ceramic and a metal materials that they have the properties that we can exploit. The ceramic has a high thermal resistance and the metal has a high mechanical resistance. These splines are used to define the volume fractions, and the effective properties are computed by rule of mixtures, and we calculate them using a temperature reference, a reference temperature. So in this figure, you can see a plate with a gradation along the thickness direction. So one of the reasons for studying this type of material is the ability they have to withstand large temperatures. And in this work, the temperature effect is explored by thermal buckling analysis. So take this plate, they are clamped in 4 edges, and by increasing the temperature, the plate may expand. And since we have the constraints of displacements in the edges, it causes compressive stresses. And for critical temperature, the plate may buckle. And this critical temperature is the output of the analysis that we want to use in the optimization. So in this work, we use the particles form optimization that they have a set of candidate solutions, the particles, that are initialized in the design space, and each particle has a position. So the algorithm, it tries to mimic the natural systems, where each particle remembers the best position it has visited, and also the best position ever visited by this form. So at each iteration, the position of each particle is updated, and taking this stored information. So we adopt the stopping criterion as the maximum number of generation and the stall generation. And the constraints are handled by a stereostatic approach. So the sequential approximate optimization approach seeks to better approximate the response of the surrogate model in regions close to the optimum by adding new points in these regions of interest. So we start with an initial model based on a small sample that is improved as the optimization progresses. So one example of this approach is the EGO, where Kring is used as the surrogate model, and the expected improvement is used to add new points. The ordinary Kring is the sum of a constant term that represents a global trend and its localized deviations that will be considered as the realization of a Gaussian process. So in that way, the correlation between the sampling points is given by Gaussian functions. The 2 parameters we have is P, we consider as 2, and theta, we adjust it to fit our model. So this is the correlation matrix. We use this likelihood function to obtain the hyperparameters of our model, including the theta. And in that way, we construct with our prediction, the Kring prediction. So in the SAO, the selection of new points should consider the exploitation that is related to regions where the model prediction is minimized, and the exploration, where the model uncertainty is higher. So the Kring model using this Gaussian process, we can quantify this uncertainty by the evaluation of its variance. And the expected improvement is this function that we want to maximize the point that maximizes this function is added to the model. Then we update the model and we repeat the process. So in this figure, we have this true function and we have this model prediction. So we initialize the model with 4 sampling points, and then we add a new point that maximizes the expected improvement. And eventually, by adding new points to the model, we find a very way to represent the true function. So in the numerical example, we seek to maximize the critical temperature. So we consider a clamped squared plate, and the volume fraction gradation is defined by a B-spline using 9 control points, and we consider it to be symmetric to the mid-plane. So we have 5 design variables. So we also adopt a constraint related to the maximum cost that the plate may take. So we can express it as that. And it's important to say that to evaluate the objective function, it's required to use a numerical method. So it has a very high cost, computational cost. And to evaluate the constraint, however, it's not required that, and it's way much cheaper. So it will be interesting to compare the two approaches that I've presented, because the objective function has a high cost, computational cost to be evaluated. So this is the optimal design we expect to find. In the top and bottom surface, we have it's fully ceramic because the volume fractions of ceramic is 1, and at the mid plate it's fully metallic. So the comparison was made by using different particles for PSO and different sampling points for the surrogate using the surrogate models. So we can observe that the results, all the optimizations found, the optimal design, and the errors was really low. It is not significant. So we can actually compare these two because they had very good results. However, when I take a look at the execution time, we see that the SAO was way much more faster. In this first comparison, it was around 10 times faster, and finally, in the third comparison, we have 25 times faster. So in these pictures, we can observe how the constraint and how the objective function improves among the iterations. So in the SEO, we can observe that it finds the global optimum and the active constraint very fast in the first iterations, and all the optimizations stopped using the stall gen criteria. And for PCO, even though it finds the global optimum and the active constraint, it takes much more longer, and all the optimizations stopped using the maximum number of iterations. It's also interesting to mention that each time we add a new particle, it may result in multiple high fidelity evaluation, because each iteration requires a new evaluation of the objective function. And for SAO, when we add a new point at the initial sample model, surrogate model, it will be evaluated just once. And the strategy is to evaluate just a new point per iteration. So we can see that the SEO is way much more faster, way much more efficient than the PCO. And so in this work, we compared the SAO and the PSO approach by taking different population sizes, and we observed that when we add a new particle to the swarm, the execution time of the PSO was significantly increased, which not happens for the SAO. And so the SAO approach proved to be an excellent alternative to reduce costs without compromising the results if we compare it with conventional algorithms. So in other cases, the convergence was faster, requiring fewer high fidelity model evaluations. So that was